Now it's not just magnets that have magnetic field lines. Did you know that? Something else has field lines too. Wires have field lines. This cord makes magnetic field. This cord makes magnetic field. So let me make the screen come back on there. So yes, this magnet, they call this a permanent magnet because the magnet has no on-off switch. It's permanently on. I put it in my cabinets and it'll be on until next year. This is a permanent magnet. The magnetic field is always on. However, this makes magnetic field too. Weak. It's weak, but it's there. And I can turn this on and off. I mean, I just turn it off. I unplug it. Then the magnetic field turns off. Now it's back on again. Has a field line. Now, let's talk about where is this magnetic field going. Let me get some extra cord here so I can have some slack. Now, there's no field line going through now because it's off. So, if this was on, the electricity would be going towards the projector here. Towards the projector. Here's the projector. It'd be going towards it. What you do is the trick, and you don't need to know this in 8th grade. In high school or college, they might want you to know this for tests, but they travel around the wire in circles. You take your right hand. Did they go clockwise or counterclockwise? You take your right hand. If you use your left hand, you'll get the wrong answer every time. And then you point your thumb, your right thumb, in the direction of the electricity. The electricity is going towards the projector, so I take my right thumb, I point it towards the projector, and whichever way my fingers are curling, that's the direction of the magnetic field circling the wire. All right, and then what you can do? See, so when this is on, electricity, magnetic fields, electricity is going this way. The magnetic field is going left, circle, 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 circling around, getting nowhere, just going in circles. But it's all weak. It's all very weak. So here's what they do. They want a strong magnetic field. Why would you want a strong magnetic field? Because you like magnets. You might have a job for a magnet. You might want to make a motor with these fields. We'll learn about that in the next video. What they do is they loop the wire like this. They loop and loop and loop it. When you loop it, see, you could crumple it all together and say, look, I got all my magnetic field in one spot now. Except some magnetic field would be going the wrong way and fighting the other magnetic field. But by looping it, and that's the word they use, loops, now the magnetic field all is working in harmony with each other, and it can build on each other. And then you have all that magnetic field in one spot. That's what they've done here. This is called a solenoid. A solenoid is, all it is looped wire. It's basically how you buy a wire when you go to the Home Depot. It all comes in a coil. Well, here they made it a really fancy looking coil, but it's the same thing. And then you run current through it. And all the magnetic fields pile up and make it a strong magnetic field, like an electromagnet. You can turn it on, you can turn it off. All right, so one of the things you can do, and what we're trying to do is work our way towards electricity here. How do you make electricity? Because we're going to make some electricity sometime soon, next class. You send the electricity, well, let's talk about, also want to talk about how you make motors. We're also working our way toward motors. When you send electricity, you can pretend this is a wire. It says electron beam. And you can download the notes. Download the notes. I hope you downloaded the notes. You send the wire, pretend this is a wire going through a magnet. When the electricity gets to the magnet, it'll get pushed. It'll get pushed, and it can either go pushed into the magnet, the wire will get pushed down into the magnet, or pushed up out of the magnet. Why? We have a magnetic field here, right? This is a magnet, has a magnetic field. And then we have a wire. It has a magnetic field. So how many magnetic fields do we have? We have one from the magnet and one from this electrical wire. So we have two magnetic fields. If the magnetic fields attract, it will dive down into the magnet. So I like you, magnet. If they repel, it will jump out of the magnet and fly out of the magnet. So what we're accomplishing here is movement. We have a permanent magnet that just sits there all day, and we have an electrical wire which electric wires just sit there all day. So you have your extension cord. When you plug it in, does it go jumping all over the place? It just sits in there. But if you put the two together, if it's a strong enough field, the wire will move. Or maybe the magnet will move if the magnet's lighter weight. Maybe it'll do the moving. But you can create movement out of two stationary objects, a magnet and a wire. Together, this magnetic field and that magnetic field can create movement. So what? This is how your electronics work, how your electric motors work, how your garage door opens and your blender blends and your ceiling fan, and your hair dryer dries. All those motions happen during, the electrical motors because of the fields pushing off each other. We'll talk about how they set that up, how they engineer that into a useful motion. There's a way to figure out whether it's going to jump up or down. It's not important for us to know. It involves using your left hand. You can look at if you really want. So you can throw the wire up or throw the wire down. In this case, they're shooting the current through to the right. In this case, they're shooting the current through to the left. And it doesn't matter. I'm not going to quiz you on which direction will it go. That's some things that some classes do when you get to a higher level. But you don't need to know that. But just know you can throw the wire up or down by changing the current. Or you can just turn the current off and have no movement. That's how your toys work. What about a permanent magnet? How do those magnetic fields work? Here's that permanent magnet. Inside this magnet are mini magnets. Atoms, clusters of atoms that are all lined up with their protons facing one way and their electrons facing another way. Protons pointing one way, electrons pointing another way. When they do that, all of their charges row together in the same direction and you have a magnet. Now, a magnet can be made out of certain metals, not all metals. Your aluminum can that you drink your Coca-Cola out of doesn't stick to a magnet, does it? Stick a magnet to it, it won't work. So, not all metal can be a magnet. Iron is a big one that we like, and nickel, cobalt, samarium, neodymium. These are really cool materials that you can do this with. But what are they doing inside? What is the machinery inside the magnet? When you just find a regular piece of metal, a regular piece of iron, do I have a regular piece of metal sitting here? Here's a piece of copper. All right. Or here, let's look even more regular. Let's not use a copper piece of metal. Look, I got this projector here. This is not a magnet, but it could be a magnet. Right now, what it is the metal, all the clusters of metal, the domains, the clusters of atoms, some of the charges are pointing up, and the little mini magnets, some of them are pointing left, right. They're not working together. But if we organize these, they would work together. They'd be like rowing a boat together. Let's explain that. Let's show you with this demo here. So I'm going to take this magnet. Okay. Now I'm going to take another paper clip. Oh, now wait a minute. How is this one sticking? If this one is sticking, then it must have been sticking to this one. This one must have been a magnet. And this one became a magnet too. Now, you still don't believe me. This magnet arranged the atoms in this paper clip. It turned that on the left side of the page to the right side. Watch this. Okay, watch this. It's cool. Oh wait, didn't work. Let's try it again. I'll be more gentle. Even more. Come on. Come on. Okay, maybe it'll work. What? It stuck because it became a magnet. When I touched this to it, it rearranged. Now I can't see the atoms. It's rearranging those clusters, those domains, and magnetized it. So whenever I stick a magnet to a piece of metal, if it can be magnetized, it will rearrange them. That's how magnets stick to your fridge. They stick to your fridge because it rearranges the fridge and turns it into a magnet. Hey, and let's do this. This is also pretty nifty. Okay, I'm going to take this, and I'm going to do this one. This is red on top, blue on bottom. Let's do this one, red on bottom. Now, this one made that paper clip just like itself, blue on top. Now, will these like or dislike each other? They like each other. Oh, now I'm holding paper clips. Now, if I go this way, blue on bottom, now it rearranges it so that this is like having red and blue on bottom here. Will these like each other? No, they don't like. They repel. Hold hands. Come on. Come on. Social distancing. All right. So they don't like each other because they arranged themselves to be just like themselves. He arranged himself to be blue on bottom, him blue on bottom, so now the blues are on bottom even on the paper clips. They don't like each other. Can you, could I cut this red and blue magnet in half? Just have a blue magnet? Could I just cut this? Just have just sell blue magnets and just sell red magnets and you can buy the complete set? No, if I cut this in half, it'll have a new red or a new blue. It's like cutting a coin in half. If I want to flip heads every time, can I just cut off the tails? And now I'm going to flip heads every time? Because I cut the tails off. There's no tails, so I'm going to get heads every time, right? No, it has a new tails. So I cut it off. There's always two sides to every coin, even if you chop off Lincoln. All right. So if you cut a magnet in half, you still have both sides of the magnet. It's a smaller magnet, it'll be weaker, but you still have a magnet. And then how does one magnet attract another piece of iron that's not magnetized? It organizes it. It magnetizes it. Now, one of the things, if you want to ruin an atom, a magnet, if you want to ruin a magnet, hit it around, bang it, drop it, heat it up, put it in the oven. Use magnets on something that gets hot. That ruins the magnets because it loosens the atoms and it's almost like they're melting into randomness by dropping it, hitting it, and smacking it around. Now the Earth, we did not invent magnets. The Earth creates magnets, and one of the things it does is the lava swirling around inside the Earth, swirling around, it creates magnetic fields. And that magnetic field shoots out around the Earth, protects us against X-rays. The Earth is a cocoon. We have an ozone layer protecting us from ultraviolet light. And we have an atmosphere to breathe and the proper distance from the sun, a tilt for the seasons, and a moon for the tides, and also it helps us know the times and the dates so people would know when to plant their crops. We also have a magnetic field that protects us against X-rays. If you travel outside of this magnetic field, you no longer have the protection of our magnetic field, and then that would increase your chances of cancer and things like that. So now, when magma cools, these fields sometimes will create magnetic rock. They're called lodestones. Lodestones. So I'm a gladiator walking through on my hike, carrying my sword, and I'm like, hey, look, Bill, this rock is sticking to my sword. Oh man, keep that. Can I have that rock, man? Yeah. But you see, they would have the metal. They'd see these lodestones, these magnets that formed. And it would form lined up in the same direction as the Earth's fields were. All the north poles were pointing the correct direction, and the south poles the correct direction. All lined up. Sometimes we find lodestones backwards in the Earth. And when we find those lodestones backwards in the Earth, we wonder, why are they backwards? Why were they built backwards? Shouldn't they be lined up in the same way that the North and South Pole were lined up? And so we find these rocks backwards. Now it could be that the rocks did a flip and the Earth just folded itself and took that layer and pancaked them over upside down. Could be. Except that we find across the whole Earth, all of that layer, they're all backwards. And so either all of that ground at that exact layer globally all did a pancake, or something else global more likely happened, something inside the Earth changed its it changed the magnetic fields. So these magnetic fields do switch. They even moved not that long ago, just a couple of degrees, and everybody's compasses were a little bit off. So they do move these micro adjustments, but over time they can do a whole 180 flip sometimes, and that would have made all the rocks backwards back then, backwards to how we have it today. They just got trapped in the hard rock. All right. And then they create solar lights as well. You go out to Fairbanks, Alaska, and that's where you have all this extra magnetic field, And it's all concentrated, and it's extra atmosphere for the light to travel through. Remember, light is electromagnetic spectrum. Now, the electromagnetic light hits this magnetic field and gets distorted and pushed. You're going to have to do that way up north near Fairbanks in that latitude, and have to be in the winter for it to happen too. All right, so with that, the tilt all just right. Let's take a look at some electromagnet stuff. What we have here, I talked about it earlier, you loop the wire, and that's called a solenoid. And then you run a current through it. Now you have electricity. That's great. But you also have a magnetic field. And since you looped it and squished them all together, you have all that magnetic field in one spot. What you do then is you take a piece of metal and you put that in the solenoid. That magnetic field magnetizes the piece of metal. Now you have this magnetic field and this magnetic field working together. And you can turn it on and off. So electromagnetics are cool. Magnets are cool. Now, you might say, well, when do I ever use an electromagnet? All the time. Every time you use an electric motor. Look here. I take these things apart with my kids a lot. Just old stuff that breaks, just to look at the wires inside, reverse engineer. So next time a vacuum cleaner or a blender breaks. Here I have, this is a coil of wire. This is from a food processor. You see the coil of wire? They looped it, and they did it on this end, and they wrapped it around metal. So when they electrocute this metal, and this becomes a magnet. And then it turns this metal into a magnet. And the same thing's happening on the other side. And then ultimately that's going to push on things. We're going to talk about that in the next video. And it's going to push on things, and that push will ultimately engineer a turn. And it spins the blender. And here's, I think this one's from a vacuum cleaner. I'll show you a whole bunch more. But you see these coils of wire. They're all in the housing of all of your electric motors, all of your kitchen appliances that you have laying around the counter and in the cabinets, and also in your garage with the drills and the saws and all of those sorts of things, circular saws, chainsaws. There's coils, the weed whacker and all that. There's all these coils of wire in there, of copper wire, and that's wrapped around metal. All right, and if you want a strong electromagnet because you want to have the best power drill or whatever, then you make more loops, more electricity, and you use better materials. You don't use the cheapest metals and the cheapest for the wires and for the electromagnets, and you want thicker wire as well. Okay, next video we'll take a look at motors and generators. I'll see you later. Boop.